So, digital security by design, who's heard of it? Yeah, there we go. We're getting there. But this was an audience that I would be surprised if I didn't. I did with that at Cyber UK, and I think I had about 5 hands in the whole audience of nearly 300. Yeah, Charlie put his hands up, which is good because obviously it's a couple of years old now, and I'll give you a bit of history of where it came from, where it's going, and what it's trying to do in a moment. But I think it's always interesting to think, this was referenced earlier, or things around this. Who's read this paper? It came out, I think, Department of Energy, wasn't it, over in the States? So 1972, October, they basically were realizing computers were going into an awful lot of places, and they had a look at them and they weren't very secure. There was all these horrible things that they could do that didn't really protect anybody and would cause issues. Now, at that point, it was fairly theoretical that you could actually exploit a buffer overload. But the paper itself became a recipe. And guess what the recipes cause? So here we go, so the reference to the PhD down there that did it. That's 72, somebody found it, and then they've basically been going through the list, working out what the mitigations for all of those documented issues are ever since. So do you think we're there? Do you think we fixed it? You know, how many years later are we? Yeah, well, nowhere near is the truth. And here's 3 papers that have been going out in the last couple of years where they've been looking at particularly the class of errors on memory safety. And I presume everybody here knows what a memory safety issue is, yeah? Oh, not as many nods. So it got introduced at the beginning in terms of the buffer overflows and things like that, but there's an awful lot of other things around it, like attacking the return address pointer and things like that. But the idea that, unfortunately, back in the, was it about 47, somebody said, this register can point to a location. And basically that's been it ever since. And there's no semantics other than it being an integer value that you can do what on earth you like with, and your memory is just a flat address space. So basically you break into anything that can be an integer in a computer and the game's over. So it's quite unpleasant. And you know, these are some fairly big ones. I quite like the Microsoft ones that basically, you know, the bit after that says 70% of the CVs that they've had to patch have been these memory safety issues. And if CHERI, what we're going to talk about, existed, we wouldn't have had to, which would have been a really nice outcome. But so is it getting better? No, it's not. So you can see the NCSC chart or the CVE charts. They're basically saying it's getting a lot worse because, of course, a lot more people are writing a lot more software. And I've not found anybody yet, even in the high assurance world, that will say that they write bug-free code or that people always use it in the way that they anticipated it would be used. So if you take those 2 criteria in that we'll never have everybody in the world building software that's bug-free, then we're always going to have these vulnerabilities. So how can we get by design of the thing that runs that software something that will actually start protecting it? Now, the big problem, therefore, is today the whole world and everybody who uses software has their own responsibility for their system, okay? So it's best practice education of the entire society with all their variations of their systems they use. Doesn't scale. It's clearly not sustainable with the number of people that are having to run around day 0 to patch something like log4j, etc., yeah? But that's all they've got, okay? But as I've obviously mentioned, the more software means more vulnerabilities. But if we sort of start looking at the stack, and the cyber pyramid is something I've been using to try to communicate, if you can start at the bottom, you've got an explosion of effects. So if we can fix memory vulnerabilities with the actual way a computer architecture implements accessing to memory, I couldn't get to 5. I could get to x86, ARM, RISC. We can go and name in sort of the ARCs, Coldfire. I can't think of what the other ones would have been, but PowerPC was the big one there as well, yes. But yeah, the percentage-wise, as we'll see in a later slide, I say there's about approximately 1 different ways of accessing memory in a computer architecture. There might be 2 if you go to things, and about 3 main CPU architectures. So if you can fix that architectural approach and make it consistent such that it goes all the way up to the billions of users, that's really what you want to do. So back in 2018, that discussion that was mentioned earlier where somebody at ARM talks about somebody in Cambridge, funny that they're in the city, but they did actually eventually talk and said, well, this is quite interesting. The folks in ARM that had those discussions went up the stack and said, oh, we really like to add this to the architecture. The answer was, no, not commercially viable, basically. There's no way that we can make that level of disruption and change to our customers. How do we fix that? Now, at that point, I was in research. I'd been fairly successful in getting money for other things. And Richard, the chief architect, said, John, can you find me some money so we can go and prove this to our customers that it works? Now, I'd done about 70 million out of the EU, 13 in my group, etc. But I said, how much do you want? He says, 40 million. Okay, so who's here done a bid where one partner gets 40 million? Yeah. Luckily, the government at the time was asking industry how can they help with quite a big pocket of money called the ICF. And we put a bid in called Securing the Future. So not secure by design, that would have not been my choice. I try to put the D on the end of that at the moment, secured by design, just to make it a bit more realistic. But we started trying to secure the future. And the funding actually came through. I asked for 120 million, because why not if you want about 40 or odd. Left arm and actually ended up running the program. So that's why I'm now the directory of the program delivering what was Securing the Future, which is now Secure by Design. And obviously one of the first things you do when you join the civil servants is try to work out how to talk civil servant language. This was my attempt at talking civil servant language of, by a specific date, something or somebody is actually going to do something for real that the government cares about. And what the government cared about was the fact that the market couldn't fix this themselves, which, as you heard earlier, was pretty self-evident because we had government saying it's been there since the 70s. It hadn't been fixed. And we were going to do it by bottom of the stack, radically updating the infrastructure at the root. And for the first time, and this was sort of the tagline, starting at the hardware upwards. And that's where, obviously, the position of ARM in the market made this actually quite an interesting program, that it wasn't just a research, can we find a way of doing something? It was actually, can we help ARM and other companies that build instruction sets find a way through the Cambridge CHERI research, which we'll obviously talk about a little bit later, to actually go and change this. And I remember one of the first workshops I did says, it's my job now to go and change the world again. So next part is then obviously the cross-cutting activities that we had to define as a delivery plan. It was no good having just come out of ARM, say, ARM, go and solve that now, here's your money. We had to actually think, well, actually, ARM plays obviously a fairly vital role in the program, but they're not, if you like, locking that IP up in any way. So we structured the program such that the core essential IP is all open source. We've published that paper on what all of the mechanisms are to do that. There's a version, actually DARPA-funded version of that for how that would fit into RISC-V, for example. So anybody who's got any voice in the RISC International, there's already a spec that says how to add this stuff into the RISC-V architecture. And obviously, any opportunities to get into other large architectures, we have that little chat if we can. But back to the delivery of the DSBD specifically. So the market failure that you heard about earlier, or the catch-22, or whatever you call it, is, will somebody build a new chip that probably costs them tens, if not hundreds of billions, when there's no software that will run on it? No, they won't. Will any software vendor write some new software for when there's not a chip? No, they won't. Will they change everything? No. So how do you incrementally move this? How do you enable it? How do you get, basically, the people higher up the stack worrying about the things down the bottom of the stack and getting those interfaces talking? Well, we go and prototype it. So we actually build an enabling platform prototype, and then obviously distribute that through the technology sector, where we look at which companies and academics can actually extend the ecosystem. I reckon we're up to about, if I was to count, we got, I think, 150 at our last all-hands ecosystem meeting. I reckon we're over 300 at the next one, and they're just the ones that come to the meeting. So we've gone from the couple of people that chatted and thought, wouldn't this be a good idea, to now actually going international, but at least in the UK, we're well up into the hundreds of people looking at this technology. And then the last part of the program was all well and good, back to the question that was posed earlier, but who cares in the industry? They're not going to care if they don't want it, yeah? So how do we get the industrial sectors caring that it actually makes a difference to them as well. So you'll see when at the end I'll introduce some of the sort of the project areas that are happening in each of those activities. So realizing the technology platform, this obviously was a big undertaking by ARM. It's called the Morello program, is their activity. We'll look at that in a little bit more detail later, but that was announced, does the date on there, October 19. Okay, so it actually took a year from finance to actually starting that program. It's good to move nice and quick and agile. Anyway, thankfully, and the research that we're basically basing this Morello and the DSBD on is some research which, funnily enough, started in the 70s when somebody said, "Ooh, wouldn't it be good if the computers weren't the same as what they've been telling?" Didn't go anywhere. It lasted about 10 years. Anybody that's got a history back into Cambridge in the 70s? I think there was about 10 years of research into what was called capability hardware at that time. And obviously, picking up beginning of the decade, another group said, well, let's try again. And they've been working fairly hard on this with various milestones to sort of basically say, what does it look like? And then there's, I think somewhere in there it says, and we started talking to ARM. I think that was about 4 years ago, wasn't it? 4 or 5 years ago. Anyway, so what was it that they were looking at when they started looking at capability hardware? And obviously one of the things they didn't want to do was just say, rip up the ISA specs of the current incumbent CPUs. So they basically created a couple of principles. They started with that one in terms of vulnerabilities, that if a programmer makes a mistake, that isn't really what they wanted their software to do. So let's help them with that, making sure the programmer works in a way that it was intended, not the way the attacker wants. And we have a great quote from one of the people that was working in capabilities in the 70s. Says, the reason we didn't go any further is we could never afford the transistors to implement it. And obviously, people always wanted faster computers with more capabilities, terrible word, isn't it, capabilities? It means so many things. So basically, give us faster computers with those transistors. Don't give us safe ones. And there's the lovely Cambridge thing of cutting and pasting slides. And then the other one was, well, we've got these pointers. The last thing we want to do is let people that use them in a way that they weren't privileged to do. So there's sort of that second part of it. And it's all around then limiting who can access what memory within a process. Okay, so this is a level of granularity that you're not below what is virtual memory, basically. It's protecting a process. So if it's all about pointers, what's the easiest way of thinking about it? So we're hardware-ish people in this room. So today a CPU basically has the integer data type and different widths of it, and some of them have floating point data types. And that's it. There's nothing for the pointer data type. So if we were to create something which is a pointer, and then it's called a capability here, and set an architectural set of rules around it of what you can and can't do with it, and who can use it, and where's it come from, and where's it go in its lifetime, then the computer hardware natively can now restrict what a pointer can do, and obviously stop those problems of it just being an integer where you add some big number and go and scribble somewhere else, yeah? So that's basically what happens. So you've got your address, which is the key part of it. You then have some way of giving it a bound, which is obviously the ability to stop it walking off the ends, approximately. Some very interesting corner cases that some of our researchers are looking at because of the rounding errors in the compression. Put a permissions set on it, so you can only use it against a register that says, have I got permission to use it? And then the magic bit, if you like, that bit, is it valid? Where did it come from? Is it being created by somebody who's got the privilege to create it? All right? And that's actually hidden in the ISA. So there's nothing in what the software can do to hit that bit. Now, as we heard from Alistair earlier, does that mean it's just a next candidate for Rowhammer? We'll see. But I think they've got a couple of different ways that they've implemented that to try to make sure that you can't just Rowhammer the pointers and start toggling your valid bit. But so at least that bit worked. The other bit, I think the S, help me there, Alistair. I think that's the signing, isn't it? The sealing.
I don't remember.
I can never. I don't know where else it would be, but there's another part to the capability, And this one really is interesting for the research community because it's the idea that you seal a pointer. Now, some of the things we're seeing people do with that at the moment is, who knows what a gadget is in terms of hacking? Okay, so basically, if you were to link in a library, what's the typical thing an API will? You get an entry point, parameters, valid, check, do something. Yeah. Now, if you can obviously enter here your code and set your stack up right, you can now just do it without any of the validation checks being done. Or it might be, oh, wouldn't it be nice if I can push some data over here? Okay, there's a little function there that I can use that for. And you go finding different entry points in your code. But this basically allows you to start sealing code so that only certain code in certain regions can run and call certain areas. So you can actually start restricting. And we've got people putting this sealed automatically on linked libraries, for example. So when you link a library, they say, this is the API, this is the only memory that library can do, even if that third-party library has some explicitly unpleasant code in it, it can't get into my local memory. Okay, so another very interesting use of the technology there evolving in the research community. So 2 key principles: the fine-grained memory protection for the programs, and obviously the slides here say C, but clearly other languages may have need for that, either directly or indirectly, and there's a lot of work going on looking at what it means to Rust, for example, and unsafe usage and all that kind of thing. But the idea that we can just basically bound pointers and get rid of a whole load of the memory safety issues, and also temporal mechanisms as well, freeze after use, that kind of thing. And if that kills off the 70% of continuous bugs that we see, people can focus more efficiently on the other 30% and other mechanisms, yeah? So, it also means that who here has spent a long time searching for a memory vulnerability bug? You know, debugging, and you just sit there for months saying, how on earth do I find where this is? This just makes it a predictable crash, yeah? So your productivity as a developer goes up as well. The other side, which is, like I say, probably the more interesting in the research side, is how do I then repartition or design software in a compartmentalized way? Because clearly what happens today is, you know, you can see it in your browser where every tab is actually another process, and then you get a very slow IPC where you do have to talk between them, or if you want to do some decompression work, you actually kick off a process or set a pipe. That's the fairly coarse grain and very expensive. If you can do that as a compartment, we've got benchmarks that's showing it, you know, a couple of 100 times or so faster in terms of how the IPC works between that hardware partitioned environments within your code. So that, orders of magnitude differences on that. And again, we've got somebody working on a unikernel where they're trying to automate that between the linked libraries and things like that. So the IPC all becomes shared memory. So in summary, what you've really got is the idea that pointers are now a native data type in the hardware. You know where it comes from, you know where it's going, you knowing that it's bounded, you know that you can't do things with it that you're not allowed. Now apply all of that to your program counter, because that's a pointer, isn't it? And your stack. And you start seeing some fairly interesting things going on. And what DSDB is doing, obviously we're funding that technology demonstrator, but more than half of the funds have gone into industry and academia to answer what does this really mean to all of the software developers? Okay. Oh yeah, there you go. Lots more words, which I think I said all of that. Okay, so compartment scalability, I think I've said all that actually. Shared memory, very fast domain transitions. So I think we all know trusted execution environments, TEEs, yeah? So the idea that those today are of limited number, 1 in trust zones, I think it's 16 in Intel, isn't it, that you've got 16 separate hardware domains. You've been there 6 months, come on. But if you're doing coarse grain partitioning, you've got some fairly expensive resources that you've got to bring with you. You've got all those TLBs on the number of page table levels and all of that stuff. This actually just ends up being a register swap, and does it match the permissions of the pointers? A very, very fast frequency of transition between the domains, and obviously shared memory for the communication between it. Okay, yeah, partitioning stuff, that's all good stuff. Yeah, so the first call I put out actually on DSDB to the academics sort of had three aspects to it. One was, Alistair's gone and done this really good work. We've now got a formal definition of the ISA. What does that mean to everybody that's building tools? So we've got a load of projects that are looking at software verifiers. How do we use the additional semantics of having this additional data type inside your verifiers and things? So clearly, today when you look at a verification tool, it has to make assumptions about any stochastic and any number that could become a pointer to know where it goes, and they've got to unroll loops and all these horrible things. If you bring all that semantics of the new data type in, those tools can obviously search deeper and faster, okay, and hopefully differently as well, which they'll come to. The second one was, what does it mean to all of the existing software? And that's where obviously a lot of work is going in. What on earth does a protected pointer in a region of memory mean to a garbage collector? Luckily, somebody said, well, it actually means that the garbage collector has to change, but they're looking at that and changing that kind of work. What's it mean to Rust? What's it mean to all the things? And then the third one was my blue sky one, which is, what does it mean? Because if you think about what virtual memory was invented for, and what virtual memory is being used for today, it's hard to believe that if you were to add the CHERI capability to the processor, they'll only be used in a way that the architects thought it was going to be used. And we're seeing that, I think, already today in terms of software TEs popping up. We're seeing people putting a whole loader in where they take an executable off the disk, load it into the virtual memory, change the IPC, the POSIX that it was, into a shared memory thing, and hey presto, they've got an in-process thing, and then they're putting context switches on it just through the capability thing. So it's basically rewriting what an operating system is. We'll see where it all ends up. So ARM, obviously, as I said, key partner because of their reach into the market. If you didn't know, they sell billions of processor cores into market each year. I think it was 25 billion last year. So if we can even hit half of those in the near future, when I say near, we'll see when that actually happens, if it happens. Can't commit to ARM roadmap deliverables, of course, but the amount of work they've had to do to enable this prototype architecture is significant. Obviously, right the way up from the boot stack, we started with software models. Obviously, we're going up into the Linaro kernel. They're working with other groups in terms of getting the higher level Linuxes. They've obviously worked and done the Android stuff themselves, and there's the compilers. So that LLVM's reasonably mature out of the Cambridge work that they did for their BSD, but obviously we need GCC as well. So what does that mean? And this basically becomes the technology platform. And physically, it looks like a PC. Yeah, we ship it in 2 boxes. It's a standard ITX motherboard. Put it in a desktop or put it in a server. And we've been awarding these to our funded projects. Though there is actually other ways of getting hold of these, which I'll mention while I'm here. Might have a slide on it later, but never mind. If you're a business, the Digital Catapult's running a program for me called the Technology Access Program. They will basically give a periodic call. There's one open at the moment where they will fund you minimally and handhold you how to unbox it and get going on it. They'll also allow you just to have a board. And then there's another tier. If you go to the website called dsdb.tech, you can actually just ask me directly, can I have a board, please? And that doesn't really have quite so much governance in terms of writing reports and things, because I know businesses might not want to tell me why they want to play with the board. So as long as you tell me that you are going to use it, and when I phone you up in 3 months, you say, yeah, we're using it, then I'm happy, okay? But yeah, that gives you the access. The maturity of the ecosystem as of today is evolving, is probably the best way of describing it. We do have one group that's got a full BSD graphical GDK stack up to UI, all converted into CHERI already. So, that was just one person doing that. So we're not talking huge code churn to get the basics running. But the real interesting bit is when you start looking at how would I refactor my code to benefit from the capability partitioning and privilege between those blocks within your code as well. So if you're interested in that, either Go to DSDB Tech, have a look at the 2 tiers or the board request. Those are the 3 ways to get into that. So a few more minutes. This is the first group of competitions I mentioned that went through EPRC. These were the 3 themes I mentioned. Each of those sites have project websites. We're working with them at the moment to really improve their distribution of information on how you get it. But you can see that cross-section of things in there that I was mentioning. The VMs is more your, not the virtual machines as in the big virtual machines, but the virtual machines for software. The top one's physical virtual machines, but there's your TEEs, operating systems. We've got one done there. How does it work with hardware security stretching out into I/O? I think you've got IOSec, which is very similar, haven't you, to the HDSec there. Okay, and Scorch was an example of one of the tooling ones. The other thing, probably not so obvious to this community, is cybersecurity isn't just a technical problem. As I mentioned, it's a social and economic problem as well. How does a company decide to do something which isn't commercially beneficial to them when it's beneficial to their customer's customer, and they're not liable for any mistakes they make? The whole environment of that, how's legislation work to sort of get that flowing through? So we did actually put a fairly large project, $3.5 million, through the ESRC, which is the Economic and Social Research Council, which is one of the other UKRI councils for distribution. They've been doing devolved spending, which basically means they've been asking their community the questions that have come up as the program runs as well. So it's not just been I wrote the question to start with ESRC, but they've been asking subsequent questions as the program evolves. And then that third area I mentioned, the industrial sector side, this is the currently publicly announced list of demonstrators. THG up in Manchester, e-commerce, that's primarily an e-commerce Java. So what does it mean to put capabilities and compartments into Java and run e-commerce on that? It also has a SmartNIC component. So how do we extend the capability from the CPU through the SmartNIC back through? I don't know, I can't see the SmartNIC speaker, but that's what's happening in that project. 100% IT, that is a mesh VPN. So how does a mesh of computers, I don't know if anybody's looked at distributed trust when you can't trust the computers at any node. It becomes quite an interesting challenge. So that's a very similar problem they've got in the network infrastructure for VPN there. Beam is going out into the automotive space in terms of their informatics and what's it mean for swarms of machines talking to each other, as well as being hacked as a group, which gets into what was Charlie was saying. Gas, smart meters, the next generation of smart meters go 2-way. Wouldn't it be horrible if they all had the same bug and somebody could actually turn on the entire gas of everybody? Not very nice. And then the last one is actually in the data center, where they're looking at how do we merge the security requirements of IT and OT in the same system rather than having to duplicate resources through the compartmentalization. More recently, we went out with one into specific software ecosystem expansion. So that's the list there. A lot of the familiar names, which I guess once you start an ecosystem, they know how to write the bids, the evaluators, yeah. But that again, this one's really pushing up the Java to the next level. WebAssembly is there, coming primarily from a business. Okay. I like this one. This is probably my most quoted one, as you'll know. A book, an online book to help people get started, because obviously the infrastructure and documentation, again, you can get to it either at the ARM site or the Cambridge site, but you can also get a lot of our tech talks and videos and things from the dsdb.tech website as well that links off to those other things. And that one hopefully will be up in the next 6 months, which is saying, getting started. How do I start writing for capability, CHERI-enabled Morellos and things? So where are we heading with all of this? Obviously, as I mentioned, the status, if you like, of the program and breaking that market failure, that's the primary goal I've got, is can I break that market failure? What's been interesting is there's probably other market failures as well, which is we've still got big industry going, yeah, you tell me that, but you know, it's going to cost me an awful lot to refactor all of my code and benefit for that. It has been, as I mentioned over lunch to a few people, it started to appear in a lot of the government level strategy documents, which is a little worrying that we haven't got commercially available products while the government's saying we need this in all of our thing. The beauty there is that basically says it might not be CHERI, but somebody's going to have to solve these problems and deliver it if they're going to deliver their strategic requirements. So if all's good, my finger in the air is 4 to 5 years to products starting into volume markets. It's not fast in hardware. You know, by the time you've got the architecture, you're then going to build it, manufacture it, integrate it, ship, yeah. So I reckon even if they were to commit, or anybody was to commit now, RISC-V might be able to do it in 3 because, you know, it's a bit of a wild west there, isn't it, compared to an architecture that sends tens of billions. But I reckon 4 to 5 years. This program runs till March 25, so there's unfortunately probably 2 years of sustaining an ecosystem with no commercial chip, which will be interesting, which is what do we do next? Anybody with big lots of money connections? And then the other one I mentioned, the essential IP is all open, okay? So it does allow and enable adoption into other architectures. So, you know, if you work with PowerPC or need a PowerPC, there's no reason that they couldn't consider these approaches, obviously implement it their own way, but if the principles like virtual memory principle is common, it really, really helps those software communities. How many versions of Linux do you want, yeah? How many versions of Windows? It's not going to happen, so you know, it's going to become, if it's an essential technology, then it'll hopefully drive commonality of approach as well. So I can either take questions or I've got that 2-minute video. Shall I play the 2-minute video with you on, or shall I just take questions? I can do a bit of both. I think it summarizes reasonably nicely.
What this Digital Security by Design program really is about is looking at a major shift away from this cycle of patching and vulnerability mitigations to sort of a new platform.
The Digital Security by Design Technology Access Program is your opportunity to get involved.
We had one big trouble with trying to do digital security by design in 1975. We didn't have enough transistors.
He was one of the guys working on capability.
The UK can be a leader in this place. Our National Cyber Strategy 2022 is to make the UK into a leading global cyber power.
You can tell he's government.
Data breaches, spyware, viruses. The most remarkable thing is that this is still with us.
So this is the architecture.
Software, we buy it, it's broken all the time. We just don't know it's broken until people discover that, and often it's the wrong kind of people who discover that it's actually broken.
We need to stop patching things up with the cyber equivalent of gaffer tape and actually fix the foundations.
We're trying to build new hardware and software technologies that fundamentally mitigate security vulnerabilities. We expect bridges to stay up and buildings to stay up. So you expect engineers to solve those problems for you. And really, we're doing something very similar for computers.
We've got to learn to get the right balance between people, the software, and the hardware.
Cybersecurity is not just a technical issue.
There's a lot of initiatives and programs that are going on around digital security by design, but the time is now for different parts of the ecosystem to collaborate and really work together.
This is a global shift that's occurring, that we're actually trying to change the way computers run software. Let's fix those foundations.
All these brilliant people are coming together to solve some of these legacy problems and give a strong foundation for the future.
A lot of our work in the last year has been around trying to envision what future digital security by design might offer to us.
So if we look to the future, we'll all benefit from having more trustworthy computing systems in terms of areas like our healthcare, travel and transport, and in just general well-being for all society.
Seeing a solution to these architectural problems that are 30 years old is probably the most exciting thing I can think of in computing.
Thank you.